Good morning. Welcome to Krishna's classroom. Now we look at another fascinating problem. Now this concerns the bounded linear functions on normed linear spaces. Let us motivate the problem by looking at the how it manifests on finite dimensional normed linear space. Okay. So let us take a model for that. A model for that is Rn over. Consider Rn over. It's an n-dimensional vector space over therefore it has a basis. We take the standard basis, and this is not necessarily one can work the same theory with any arbitrary basis. So we take E1 En is a basis for R, where Ei is equal to so this is the standard basis for Rn. This is the standard basis. Now we consider any element x Rn, then x is x1 E1 En, where each xi belongs to equal to 1 to n is the unique representation of x with respect to or in terms of basis. Therefore, we often write x equal to the n tuple to mean that x is represented by x1 E1 plus x2 E2 plus xn En for every x belonging to okay, so this is an n tuple. This is the coordinate, the representation of x with respect to this. Now we define a linear function on Rn as a map from Rn to Rn to R, where R is the associated field. So in a general case, it will be, if you are considering a finite dimensional vector space, it is defined over some field, and then that will be the map from the vector space into R, such that it is linear. That is, there is a map phi from Rn to R. Phi is linear. Then this is called, phi is called a linear function. Okay. Now one immediately, so what are things you have? Now you see that phi of x equal to x1 phi e1 phi x is equal to x1 phi e1 plus etc. xn phi en. Therefore, phi is completely determined by the values it takes on E1, E2, etc. Okay, so let us write y designate the n tuple okay, then phi x is equal to sigma xi y ei, which is equal to sigma xi okay. That means that is phi is identified with the vector y equal to phi e1 and this is an element of R. Therefore, we have identified, so corresponding to phi, that is phi is identified with y. Now you can see that this is unique. Now this identification How do you prove that? Suppose there are y tilde is another of 5. Then if y tilde is equal to y tilde 1 with respect to the basis that we have chosen, we have sigma xi, phi ei is yi. Okay. Xi yi equal to sigma which implies equal to 0. Now this result is true for every x, and this is true for what does this mean? Which implies I can write this as which I can write as standard notation. Where x is equal to n tilde. Okay. Now, and this is true for every x. Therefore, zero. I want to say this is equal to 0. Okay. That is and that means Therefore, therefore, the representing vector phi is represented by a unique vector. In fact, we designate is a vector space of dimension n. So this is what is called the dual space. You shall also observe the following. Defines a linear function on Rn, that is an element of Rn prime, the dual of R, by okay. Therefore, together Rn prime is isomorphic to a copy of the dual of is isomorphic to R. Okay. That is, this identification of phi with y is the corresponding isomorphism. to the usual dot product, which is equal to sigma. Therefore, you see that the dual space consists of all linear functionals over Rn is identified with elements in Rn. In fact, Rn becomes a copy of the dual space through an isomorphism. And the isomorphism is defined. So, every linear function on Rn is now identified with a vector in Rn, and every vector in Rn generates an isomorphism. Now, this is what happens in the finite dimensional spaces. I want to make a few remarks. Since we are working on a finite dimensional space, we don't have to bother much about a norm. Okay. So, suppose Rn is with some norm. Now, one observation that I make is all norms are equivalent on, for that matter, any finite dimensional vector space. Norm endows the space with a metric, and that metric defines a topology. Therefore, Rn becomes a topological space once you choose a norm. Now, there are different ways in which you can choose the norm on this space, and the famous or the most common one is the usual L2 norm. The other norms are, in general, these are all norms on this. Infinity. Okay, these are all norms on. So there are different norms on the space. Depending on that, the geometry of the inner geometry of the space will be solved. That's the interesting aspect. Okay, so this gives different geometry. However, topologically, whatever that you see as an open set in one norm is also an open set in other. Therefore, the topology defined by all these are the same. And of course, another norm is this, generally used. So these are all different norms on the space. So infinitely many norms that you can endow the space with. So it become a normed linear space. However, on finite dimensional spaces, more generally on finite dimensional spaces, all norms are equivalent. In the sense that they generate the same topology. That means the same open sets. Is the same open sets. Therefore, topologically, all these spaces are equivalent. Or when you talk about continuity on this space, then with respect to if some function is continuous with respect to one norm, it is going to be continuous with respect to every other norm. So this is one of the preliminary analysis that we present before you. So essentially, Rn itself manifests as a dual of Rn. More generally, if X is a n-dimensional vector space over a field, over a field F, then X prime, the class of all linear functionals on X is isomorphic to now this is the general result that we have, and somehow the topology does not come into the picture and it's not necessary to consider. Even otherwise this general result is valid without the consideration of topology. That is our conclusion from this discussion. So naturally, the question comes, what if the space is not finite dimensional? So the question that comes up at this stage is this. What if the space is infinite dimensional? Is this result valid on infinite dimensional spaces? Okay. Let us explore this. At this stage, I have a caution. When you deal with infinite dimensional spaces, dimensional spaces, often infinite sums occur, which cannot be justified with the vector space operations. Because in a vector space, you can talk about finite sums. Okay, there is no problem. But the moment you write an infinite sum, you have to give a meaning to it. But how do you give a meaning to it? You give a meaning to it only uh, by using a notion of convergence or a topology for the space and so on. Okay, so this requires where the concept of convergence of sequences which needs a topology. On the space. Therefore, often a norm topology is made use of. And there are situations where you talk about topological vector spaces where the topology does not come from a norm. But a norm topology is quite often used where you can generalize whatever we had been doing in RL. Okay. And there is the path that you have to take is then fairly clear. So, but the problem that you have is that a the same set of objects with one norm is not the same set of objects with a different Now let us take an example. See this. Okay. Now, irrespective, see, we made a statement that in a finite dimensional space, irrespective of what topology you use, it is the same. Okay, right? You get the same topology. Whereas, say, for instance, Rn, you use this L1 topology or L2 topology or LP topology for any value of lying between 1 and infinity, they all create the same open sets in the finite dimensional spaces. That does not happen when you come to infinite dimensional spaces. I will give an example. So consider the infinite of real numbers. So we take x as r. Now we define two norms on that. Now let us define two norms on that. Alright. See, norm defined as and so these are two norms on this class which essentially throws out certain elements from it. For instance, if you take the sequence 1, 1, 1, 1, 1, etc., it is neither, see, if we take, suppose you take x to be that means all elements are 1. Then infinity is not finite. Infinity. Whereas now you take another element y which is equal to 1, 1 by 2, then you see that sigma xi is again infinity, whereas sigma is finite. Okay, so this particular element is in the space with this norm, whereas it cannot be the space with this norm. That's the difference that you have. So this is, there are two, so this is called L1. So we will now make it more clear. So let me define L. And sigma one can show that this is an infinite dimensional vector space. So also L2 defined by etc. and sigma finite. Now in L1 you define the norm. So you take L1 with 1, L2 this is not the same as this. Now you see that the sequence 1 by n does not belong to L1, whereas L2. So the two spaces are different. Okay, right? Therefore, you can actually show that L1 is contained. Okay, this property you can write. All elements in L1 are also in L2, whereas there are elements in L2 which are not in L1. So these two spaces are different. Therefore, in this case, so this is something that you should remember. So in general, all the LPs are different. Okay. So this is something that we observe. So each one has to be treated separately. Okay. So what we are going to do in this series of lectures or in these lectures is to look at the same problem that we have seen with the finite dimensional spaces, namely look at all linear functionals over infinite dimensional spaces. That includes the finite dimensional case also. Okay. Infinite dimension normed linear spaces, and then determine what are the dual spaces of a given space. can you identify with some concrete spaces? For instance, if L1 is given, L1 dual is there. The dual of L1 is what? A set of all bounded linear functionals on L1. And you ask the following question. What is do you have a representation theorem that you have as in the case of finite dimensional space? In the finite dimensional spaces, we have identified a finite dimensional vector space. Its dual can be identified with itself. But is it possible to make a statement of this kind in this case? Okay, so you raise the same question here and then try to find out solution for this. Okay, so that is going to be the theme for our discussion in the next few lectures. So let me just call this talk normal linear spaces 1. Finally, you want to explore this. Actually, what are the represent? Is there any represent given a linear function on an infinite dimensional space? Do you have a vector in the space itself representing it, or in some space representing it, or what is the concrete form of the dual space of a given space? So the question that we have is this. Given a normed linear space X, X prime, the dual of this is the question that we take up in our lectures. I think it's a nice place to stop, and we look at what is called LP spaces. In our future lectures, we look at what are called LP spaces. We'll take care of all this once we introduce the proper measure and so on. That is not difficult at all. So that will be our topic for discussion in the remaining few lectures. Okay, and finally we prove the so-called Rees representation theorem. That means the representation theorem. Okay. Thank you very much. What is the representation theorem? Given the linear function, you identify with a vector. But where? This is the question. Okay, right? So let me just do some little bit of drawing, which will give you some insight into what's happening. So in the finite dimensional spaces, this is what you have. This is your R. This is your R. And now we are talking about linear functions on Rn, which are nothing but maps from Rn to R, which are linear. Okay, or I will put it this way. Better to what I can say is that to take an X belonging to Rn, you define a space of all linear functions Rn prime. Now this is a phi that maps X to this is the vector X to R. Okay. Now what we are proving is this. Okay. This is the same as you have another copy of Rn. There is a vector y belonging to Rn such that y, this is xy, maps to the same image. So this is phi x equal to, therefore phi is identified with phi. This is an isomorphism that you are defining. Okay? So phi is now identified with the particular. So each phi in Rn prime, there is a corresponding y, so that a particular linear function is determined by, this is what you call your familiar dot product, okay, through the dot product, and that's equal to x dot y. Okay. So this is what you have. How this particular result manifests in infinite dimensional spaces, where you suddenly require a norm, an infinite dimensional normed linear spaces. So this is the question that we are going to address in our future lectures. Thank you very much. It's only an intro.